This online tutorial is about Lewis acid-base strength. Like Bronsted acid-base strength, Lewis acid-base strength is very important in context of acids and bases. This is due to the fact that Bronsted-Lowry acid-base theory and Lewis acid-base theory are the two most common acid-base theories in chemistry, and it is very important to be familiar with essential concepts of these theories. Indeed, acid-base strength is an essential concept of these theories, since acid-base strength plays major roles in many acid-base phenomena like direction and extent of acid-base reactions. We've already discussed that based on Lewis acid-base theory, acids are capable of accepting an electron pair and bases are capable of donating an electron pair. Or in simple words, a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. In a Lewis acid-base reaction, a Lewis acid and a Lewis base react each other to form a Lewis adduct. Lewis acid strength or Lewis acidity is the thermodynamic tendency or ability of a Lewis acid to act as a Lewis acid, that is, to act as an electron pair acceptor. On the other hand, Lewis base strength or Lewis basicity is the thermodynamic tendency or ability of a Lewis base to act as a Lewis base, that is, to act as an electron pair donor. Lewis acids and bases with higher acidities and basicities or stronger Lewis acids and bases are better at formation of Lewis adducts and therefore more stable Lewis adducts. Lewis acidity or basicity can be expressed both qualitatively and quantitatively, where a qualitative expression gives an order of relative acidities or basicities, like Lewis acid A is stronger than Lewis acid B, Lewis acid B is stronger than Lewis acid C, and so on. On the other hand, a quantitative expression gives numerical values for quantities associated with acidity or basicity. Quantitative expressions not only include qualitative expressions, but also they are usually much more powerful. There have been a tremendous works to develop measures for Lewis acidities and basicities. For example, a recent book in this field with the title Lewis basicity and affinity scales, data and measurement, published in 2010 by Wiley, reports about 2,400 equilibrium constants, 1,500 enthalpies, and nearly 2,000 spectroscopic infrared and ultraviolet sheets gathered together in more than 20 thermodynamic and spectroscopic scales of Lewis acidities and basicities. Here I'm going to discuss common terms and quantities for Lewis acidity and basicity. But before we proceed to such discussion, like Bronsted acid-base strength, here also it is very important to note that whenever we want to consider a quantity to measure Lewis acidity or basicity, we should pay attention to the free watts in the following sentence. It measures watt for watt. At what situation? Here, the first watt points to the quantity used to measure acidity or basicity. It is common to use thermodynamic quantities enthalpy change, delta H, equilibrium constant, K, and Gibbs energy change, delta G, to measure acidity or basicity. These quantities have different properties, and it is important to pay attention to such differences. For example, both equilibrium constant, K, and Gibbs energy change, delta G, include both enthalpic and entropic effects, while enthalpy change, delta H, doesn't include entropic effects. The second dot here points to the chemical species under analysis. For example, is it a Lewis acid, and are we measuring its electron pair accepting capability, or is it a Lewis base, and are we measuring its electron pair donating capability? The third dot here points to the situation at which measurements are made. For example, are we measuring in a non-polar solvent, in a polar solvent, or at gas phase, where measurement in gas phase aren't affected by solvation effects, and therefore measurements at gas phase can be considered as measurements of inherent acidity or basicity. On the other hand, solvation effects can affect measurements in solutions, where solvation effects are usually negligible for non-polar solvents, but on the other hand, solvation effects are usually considerable and important for polar solvents like water. Anyway, we should pay attention to these aspects of any quantity used to measure acidity or basicity. For Lewis acidity and basicity, I'm gonna discuss equilibrium constants, person, hard and soft acid-base concept, affinity scales like antimony pentachloride affinity scale or Guttman donor number, boron trifluoride affinity scale, metal cations affinity scales, Drago's ECW and ECT models, hydrogen bond acidity and basicity, hydrogen bond acidity and basicity, and spectroscopic methods. In this video, I'm going to talk about equilibrium constants, and the other terms and quantities will be discussed in next videos. The most common way to express Lewis acidity or basicity is by equilibrium constants for Lewis-Adab formation reactions. In a Lewis-Adab formation reaction, a Lewis-Adab forms from reaction between a Lewis acid and a Lewis base. For example, Lewis acid A and Lewis base B react each other to form Lewis-Adab AB. The equilibrium constant for this reaction, K of A and B yields AB, is equal to the equilibrium concentration of Lewis-Adab over the equilibrium concentration of Lewis acid times the equilibrium concentration of Lewis base. Equilibrium constants of reactions of this type are called by names like formation constant, association constant, stability constant. It is common to denote formation constant by Kf. So, for example, the equilibrium constant for this reaction is the formation constant of Lewis-Adab AB or Kf AB. We can also consider the reverse of this reaction. For example, Lewis-Adab AB yields Lewis acid A and Lewis base B. The equilibrium constant for this reaction is equal to the equilibrium concentration of Lewis acid A times the equilibrium concentration of Lewis base B over the equilibrium concentration of Lewis adduct AB. Equilibrium constants of reactions of this type are called by names like dissociation constant, instability constant. It is common to denote dissociation constant by Kd. For example, the equilibrium constant of this reaction is Kd of Lewis adduct AB. Since these reactions are reverse of each other, their equilibrium constants are inverse or reciprocal of each other. And when one of them increases, the other one decreases, and vice versa. Instead of numerical values of equilibrium constants, we may report values of their decimal logarithm or the values of their pKs, where decimal logarithm is usually used for formation constants and pKs are usually used for dissociation constants. pK is equal to the negative decimal logarithm of k. pK is the co-logarithm of k. Therefore, k is equal to 10 to the power of the minus pk. It is important to know that having equilibrium constants is like having Gibbs energy chains, since they are related to each other by this relationship. Standard reaction Gibbs energy is equal to negative RT ln K, where R is the gas constant, T is the thermodynamic temperature, ln is the natural logarithm, and K is the thermodynamic or standard equilibrium constant. This also can be written in this way. Instead of natural logarithm, we can use decimal logarithm. Values of K and delta G can be obtained from each other with the help of this relationship. Both K and standard reaction Gibbs energy include both enthalpic and entropic effects. And many useful information can be concluded from them. For example, the direction of reaction, the extent of reaction, how good or how stable form Lewis adduct is, and so on. So we see why these quantities can be considered as the best measures of Lewis acidities or basicities. Indeed, there is a huge data of numerical values of equilibrium constants at different situations, at aqueous solutions, at non-aqueous solutions, and also gas phase, where it is hard to have ionic species in gas phase, especially those with high electric charge. Since water is the most common solvent, we have a huge data of numerical values of equilibrium constants in aqueous solutions. Higher values of formation constants means that thermodynamically this reaction proceeds to the side of products more. Or in other words, Lewis acid A and Lewis acid B are better at formation of Lewis adduct AB, and the form Lewis adduct AB is more stable. Therefore, higher values of formation constants mean higher acidities or basicities, or stronger acids and bases. Therefore, we can use numerical values of equilibrium constants to measure and compare Lewis acidities and basicities of different chemical species at different situations. Let's consider an example. For example, let's consider reactions between Fe3+, ferric, and Hg2+, mercury cations with halide anions, F- fluoride anion, Cl- chloride anion, Br- bromide anion, and I- iodide anion. The general form of the reaction is like this. Where M is the metal cation, X is the halogen, and Mx is the product. The equilibrium constant for this reaction is as follows. And it can be considered as formation constant of Mx. For example, in aqueous solutions, Fe3+ and F- can react each other to form FeF2+, whose equilibrium constant is equal to this. And can be considered as formation constant of FeF2+ from its constituents. Here, metal cation acts as a Lewis acid, and halide anion acts as a Lewis base. They react each other to form the Lewis adduct Mx, which is also a coordination entity studied in coordination chemistry. Values of decimal logarithm of K are as follows. Here, the value for reaction between Fe3+ and I- is absent, since in aqueous solutions, Fe3+ oxidizes I-, and we have an oxidation reduction reaction instead of this reaction. For example, the value of K for this reaction is 10 to 6.04. We can use numerical values of equilibrium constants like this to compare Lewis acidities and basicities. For example, in reaction with Lewis acid Fe3+, we see that formation constant for F- is bigger than that of Cl-, and it is itself bigger than that of Br-. So we can conclude that in reaction with Lewis acid Fe3+, order of Lewis basicities of halide anions is as follows. When the reference acid is Fe3+, the reference acid, the acid with which our bases are reacting. When the reference acid is Fe3+, F- is a stronger Lewis base than Cl-, and Cl- is a stronger Lewis base than Br-. In other words, towards Lewis acid Fe3+, F- shows higher basicity than Cl-, and Cl- shows higher basicity than Br-. On the other hand, for Lewis acid Hg2+ mercuric cation, value of formation constant increases from F- to I-. So, for Lewis acid Hg2+, the order of Lewis basicities for halide anions is as follows. We can also compare order of Lewis acidities. For example, in reaction with Lewis base Cl-, Hg2+ acts better than Fe3+, since its value of formation constant is bigger. So, towards Cl-, toward Lewis base Cl-, or when the reference Lewis base is Cl-, Hg2+ is a stronger Lewis acid than Fe3+. Here, we have a very important point. We see here that when our Lewis acid changes from Fe3+ to Hg2+, the order of Lewis basicity also changes. In fact, it is reversed. So we see that in general, the order of Lewis acidities or basicities is not constant, is not invariant. We can't have unique order of Lewis acidities or basicities. When the reference Lewis acid changes, the order of Lewis basicities may change. When the reference Lewis base changes, the order of Lewis acidities may change. So we see we can't have a universal order of Lewis acidity or basicity. This was not the case with Brensted-Lowry acid-base theory. In Brensted-Lowry acid-base theory, for example, when Brensted acid A is stronger than Brensted acid B in reaction with Brensted base C, we can assume that Brensted acid A will be still stronger than Brensted acid B, also in reaction with Brensted base D. So in Brensted acid base theory, we can have a unique or universal acid base order Brensted acidity or basicity at a given situation, of course. But this is not the case with Lewis acid base theory. In Lewis acid base theory, orders of Lewis acidities and basicities may change when reference Lewis acids or bases change. This may be justified by considering the fact that in Brensted-Lowry acid-base theory, the reference chemical species, the reference acid is H+. The reference acid is invariant, and because of that, we can have a universal order of acid-base theory at a given situation. On the other hand, for Lewis acid-base theory, the reference acid may change. We may consider Fe3 plus as a reference Lewis acid. We may consider Hg2 plus as a reference Lewis acid, or H plus, or many other chemical species. And because of that, the order of Lewis basicities is not constant. We may also justify this fact in this way. Brensted-Lowry acid-base theory and Lewis acid-base theory are similar in the fact that in both of them, acids and bases are acceptors or donors of something. In Brensted-Lowry acid-base theory, acids are donors of H+, hydrogen cations, bases are acceptors of H+. On the other hand, in Lewis acid-base theory, acids are acceptors of an electron pair, bases are donors of an electron pair. But here we have a great difference. In Brensted-Lowry acid-base theory, in a Brensted-Lowry acid-base reaction, H+ are completely transferred from Brensted acids to Brensted bases. And we can here separate things. We can assume that at first Brensted acids give their H+ to the medium, and then Brensted bases get those H+ from the medium. And because of this, we can obtain a universal order of Brensted acidity or basicity. On the other hand, in the Lewis acid-base theory, in a Lewis acid-base reaction, an electron pair is not completely transferred from a Lewis base to a Lewis acid. A Lewis acid and a Lewis base share an electron pair with each other in the final product in the form Lewis adduct. Because of this, the ability of a Lewis acid to act as a Lewis acid, or the ability of a Lewis base to act as a Lewis base, in addition to its inherent properties, also depends on properties of its reaction partner. And because of this, when Lewis acids change, order of Lewis basicities may change. When Lewis base change, order of Lewis acidities may change, and we can obtain a universal order of Lewis acidity or basicity. This also has another consequence. To determine the order of acidity or basicity, for Lewis acid-base theory, we will need more parameters than Brensted-Lowry acid-base theory. For Brensted-Lowry acid-base theory, one parameter will be sufficient to determine order of Brensted acidity or basicity. But for Lewis acid-base theory, we will need two parameters. For example, to determine the order of Lewis basicities of halide anions in aqueous solutions, we need two parameters. One parameter, for example, the value of equilibrium constant, and another parameter, the type of reference Lewis acid, the Lewis acid against which order of Lewis bases are compared. We will see other examples of this aspect of phenomena. For example, in Drago's ECW and ECT models later. I will discuss other terms and quantities for Lewis acidity and basicity in next videos. This is the end of this online tutorial. I hope you find it useful.